So, good morning to the survivors. I guess we can start. Can you hear me? Okay, yesterday we discussed the Hawking temperature, and we saw the consequences of the fact that black holes radiate and eventually may evaporate. Today we will take a different point of view. Again, the problem will be to study black hole thermodynamics and maybe trying to go more quantum and to understand the quantum aspects of this, and eventually to define a gravitational path integral, so a path integral where the matrix can be dynamical. So far we have considered QFT in a fixed classical background, but in principle we would also like to include the fluctuations of the matrix in our quantum treatment. So a good idea is to use the path integral. But before getting there, let's keep working with QFT at finite temperature, because we saw that there is a temperature, so we need to incorporate it in our description, and in a fixed classical curved background. So the title of the chapter is Euclidean quantum gravity, but for the first part of the chapter I'll remain with QFT in a fixed background. And by the way, there is an updated version of the notes online with most of the lecture of today and of tomorrow as well. So as I said, let's start from not considering really quantum gravity, QFT curved space. We saw that we have a temperature, so we would like to consider QFT at finite temperature and see if it has anything to do with our black hole. So let's first recap a bit QFT at finite temperature. It's probably stuff that is familiar to most of you, but it's good to have it next to what I will say later. So I'll introduce first the temperature in quantum field theory, and then also some chemical potentials, and then we will compare this with the black hole background. But so far, let's start from just QFT at finite temperature. And see how we can describe this. Sorry. So you probably know that QFT at finite temperature is the same as quantum field theory, defined on a background where the time is compactified and imaginary. So we go to Euclidean space. Suppose we are in flex space. We have Minkowski space originally, but if we want to do QFT at finite temperature, we can do a trick that is consider a theory on the Euclidean space and compactify the Euclidean time. At that point, the Euclidean time is not interpreted as time anymore, but it has the meaning of the length of this time circle has the meaning of the inverse temperature. The point is that in order to consider a theory at finite and fixed temperature, I must be at equilibrium. So everything must be time invariant. I need to have time translation invariance. And therefore, time evolution is not important. So time is like a redundant coordinate. We don't really need that. And we can use the time direction in order to introduce the temperature. Let's recall this is the case. So let's compute some thermal Green's functions, so two-point functions of some operators. So we want to compute thermal Green's functions. I'm going to define this. For instance, we could do many things, but for instance, let's take a two-point function for some operator O that in principle depends on t, and on the other coordinates x. So x here are the spatial coordinates. But as I said, we assume time invariance because we want to describe a system at equilibrium at fixed finite temperature. So we want to be in the canonical ensemble. So we assume this property of all the Green's functions. So if we want to compute the Green function between the same operator but evaluated at different points, tx and t prime x prime, well, since we have time invariance, the Green's function, the two-point function, can only depend on the difference t minus t prime because of time invariance, time translation invariance. And therefore, we can choose, without loss of generality, to take t prime equals 0. So we will have the function, the Green's function, that is g at inverse temperature beta. Now I'm going to introduce to show how the temperature appears. But it will be, without knowing anything else, we know that it is in principle minus t prime, and then x prime. But as I said, since here we have just a difference, we can take t prime equals 0. So we can take t prime equals 0 with no loss of generality. Okay, and beta here, beta is the inverse temperature. So how do we define this function? Suppose we have the Hamiltonian of our theory. We may have the Lagrangian, we can construct the Hamiltonian, we quantize it, so it's the Hamiltonian operator. It generates translations along the time direction. It's the Hamiltonian of the system. And okay, this is what it does, but at the same time, if we want to compute a thermal partition function, we want to weight each state with e to the minus beta times its energy. This is what it means to compute a thermal partition function or a thermal correlator. So we want to use, we are in a statistical ensemble. We don't know in which state our system is. We know that it's occupied with different, the state comes with some probability that is weighted by e to the minus beta 8. This means that we have a mixed state and we are using a density matrix to describe the system. So the same kind of density matrix that we had yesterday, this is the thermal one, e to the minus beta h is the thermal density matrix. This is just a Boltzmann factor, is e to the minus energy over kappa t. I'm setting kt, I'm setting the Boltzmann's constant k to 1, so it's just e to the minus beta times h. Are these familiar things? I guess so. Yes. Okay, so we can, having this density matrix, we can introduce the function, the canonical canonical because we are in the canonical ensemble where the temperature is the independent variable and not the energy. So z will depend on beta, is my independent variable, and is the trace over the Hilbert space of the theory of e to the minus beta h. This is the partition function. And in order to compute any expectation value, let's see if there is enough space here, the expectation value of any operator, or let's see, for instance, the one-point function here is 1 over z. This is the normalization, and then I have trace of O, rho times O, rho times O. This is the expectation value at temperature beta. I don't don't know if you can you see that? Well, this is the one-point function. I have the normalization, then trace of rho times the operator. Right here, anyway, the same thing. I write the same thing for the Green's function. So g beta of t x x prime will be, okay, z minus 1 trace of e to the minus beta h times O of t x, O of 0 x prime, and then I close the parentheses. Okay, this is what we would like to compute. So we assume t larger than 0 here so that we already have time ordering here. So, okay, let's take t larger than 0. Is there any question about these basic definitions? Okay, now we want to make the analogy with a time evolution. So we have this e to the minus beta h. It's not time evolution, it's a Boltzmann factor so far. But it's similar to the factor, the exponential factors that you have when you introduce time evolution. So let's recall time evolution in Heisenberg picture. Is the evolution of the operators and not of the states. So in the Heisenberg picture, is the operator at the time t plus delta t, e to the I delta t h, operator at time t. I'm ignoring the x coordinate, but it's there. E to the minus I delta t h. Okay, so now we can do a formal trick. We can perform an analytic continuation of this time evolution by assuming that delta t is imaginary. It's something that can be done if if there is no particular reason why it should not be possible a priori. So we can make this assumption that we can take delta t to be I times beta. Of course, we choose this length, this time interval in an appropriate way, so that I times beta. And therefore, our time evolution becomes an evolution in imaginary time, because we take, what we get is I just replace e to the minus beta h o t e to the plus beta h. And now we can use this into this expression. You see, you can replace this e to the minus beta h times O of t that I have here with, okay, I do all the steps, but the main point is that I can replace this expression that I have there with O dt plus I beta times e to the minus beta h. So let me just go through the steps. Okay, I take this definition and I do what I just said. So it becomes zeta minus 1 trace of O of t plus I beta x e to the minus beta h O of 0 x prime so now let's use cyclicity of the trace to reorder things a little bit. So we just copy things, but in a different order. O of 0 x prime, then we have O t plus I beta x. Okay, and then since these operators are evaluated at different points in space-time, then they commute, so I can also reorder this. Okay, for your benefit, I just recopy everything again. E to the minus beta h, O of t plus I beta x, O of 0 x prime. So what I got here is the same Green's function that I introduced at the beginning, but shifted in time, shifted in imaginary time. So we obtain, one thing I forgot, here I commuted operators. Since we may be considering fermionic operators, I said, okay, they commute, that's fine. But if they're fermionic, we get an extra sign. So let's also include this. It doesn't cost anything. We can put a -1 to the f there because of this reordering of the operators that I did. So let me copy that as well. So I have -1 to the f, and this is the definition of the Green's function, g beta t plus I beta x prime. Okay, so we conclude from the first, comparing the first line and the last line, that the Green's function is periodic or antiperiodic if we have fermionic operators in imaginary time. That is, we have what was the time evolution. Now we have done this trick, and we have an imaginary time interval, and which is precisely the period of the Green's function. Yes?
T is still a Lorentzian time.
So far it is still Lorentzian. That's why you have a relative I between the two.
But then why can you commute the operators? I mean, T is a Lorentzian time. Why are they spaced like separate?
X and X prime are different space points.
But is there no light flow? It can be at different space points. There is a difference in time, right?
Yeah, right. But yeah, I think you can, in any case, you can still do it. If, okay, you're not evaluating them at the same time, but you can still do it. If you want, this Green function is symmetric and they're exchanging the space positions. Okay, but anyway, since next step, since we just mentioned the fact that t is Lorentzian time and beta has an I in front, so it's convenient to rotate, Vic rotate our time to a Euclidean time, so that we have a time evolution that is now a Euclidean time that is periodic without an I in between. So let's do that here. No, I have not. I just noticed that there is this periodicity in temperature. Its compactification of the time is the consequence of this. So, I mean, there is no actual time circle. It's just the fact that we are in Lorentzian space-time, but we assume time translation invariance. So time is not really important. I mean, I can evaluate my Green's function at any time, and nothing changes. So I use this extra direction to implement the temperature in this way, by imposing periodicity in imaginary time. But it comes from these considerations. It's not choose. Does this clarify the question? Or okay. So, use the Euclidean time. Euclidean because it makes the space-time metric Euclidean. The Vic rotation makes the space-time metric Euclidean. And the Euclidean Green's functions, GE of tau and x, that are G of t equal minus I tau x. And so we obtain these Euclidean Green's functions are periodic in Euclidean time. Tau x prime equal -1 to the f so this is a basic consequence of quantum field theory at finite temperature. So we conclude from this argument that QFT at finite temperature T is equivalent to QFT in a Euclidean space-time, where now we have compactified, at this point we have compactified the Euclidean time with a period, and we choose the period of the compactified Euclidean time to be beta, that is the inverse temperature. So there is also, so far this was a Hamiltonian representation in the sense that I used the trace over the Hilbert space of the theory, and the trace is weighted by the Hamiltonian. But we can choose also to describe our quantum system with a path integral representation. So let's see what it corresponds to. This is the starting point. We assume time translation invariance, yes. But then the main point is this fact that the density matrix is e to the minus beta h, and what we are evaluating is originally a thermal Green's function that contains this e to the minus beta h, and we use the analogy with time evolution. So this is the main step that we do. We convert this statistical problem into time evolution, but in imaginary time, because there is no I in e to the minus beta h. I emphasize again, we are assuming time translation invariance because we want to describe things at equilibrium. So this is QFT at finite temperature, and at equilibrium. Temperature is constant, homogeneous, uniform, and nothing evolves in time. If you want to do things in out of equilibrium, then you do real-time QFT, but that's another completely different approach. So recall, what does the path integral do? So you can start from so it's a Lagrangian, for more Lagrangian formulation. It uses the Lagrangian of the theory. You have a field phi, and it is, let's say, a field configuration. I have a field, assume that I have a field phi, it can be scalar, fermionic, whatever, and I choose a field, some initial conditions. I choose the profile of my field phi at time tau 1. I already go Euclidean because we know we have to do that. So this is the Euclidean time. So, and then we have a final configuration, phi 2, at time tau 2. I could do the same in Lorentzian time, but since we know we need to use Euclidean time, let's already do that. And the path integral computes for you the amplitude to go from phi 1 to phi 2, to evolve the field starting from phi 1 at time tau 1 and going to phi 2 at time phi 2. So here I have phi 2, tau 2. Yeah, I guess I have some typos in the notes, but this is okay, here what I'm using here, this is the Euclidean action. So I for me will be the Euclidean integral. The IE will be the Euclidean integral. I is just the action. And it depends on the fields phi, and then I compute the path integral with these assigned boundary conditions. Every time you compute a path integral, you should assign boundary conditions. And this is the boundary condition assignment. This amplitude, however, is also the same since the meaning of this is that we start from this configuration at time tau 1, and we go to the configuration phi 2 at time tau 2 by the evolution with using the Euclidean Hamiltonian. So this is the same as phi 2 e to the minus tau 2 minus tau 1 h phi 1. So this is how we convert from this formulation that uses the action, that is the Lagrangian, to a formulation that uses the Hamiltonian. So this is very standard and basic stuff. So I don't need to recap how the Hamiltonian is defined in terms of the Lagrangian. Okay, things you see in quantum mechanics. This is just the quantum field theory generalization of that, the field theory generalization of that. So now we can decide that the time evolution is along the entire period beta of our compactified Euclidean time. So suppose I start from tau 1 and I end at 1 plus beta. So we do an entire tour around the thermal circle, the Euclidean circle, which is the thermal circle. So we obtain, in this way, the path integral representation of the partition function. Did I erase it? Yeah, the canonical partition function. So the same partition function that we had before, that was trace of e to the minus beta h, can also be represented as a path integral, because we can take this evolution, start from any time tau, go to tau plus beta, and so here what we and trace over all the possible boundary conditions. The boundary condition phi 1 and phi 2 at this point must coincide, because must be the same, because we start from a point in the Euclidean circle, we do the tour, we come back there, so we impose that the boundary conditions coincide up to a sign, depending if we have a bosonic or fermionic field. If we have a fermionic field, we need to pass, as we saw there, the operator from one side to the other side to come back to the original situation, and therefore we get an extra sign. So we impose these boundary conditions, periodic or antiperiodic, and we sum overall possible set of boundary conditions. This is the meaning of this trace, and from the point of view of the path integral, it's the same. It's the same as you see here, but this with prescribed boundary conditions. So it's d phi e to the minus Euclidean action. And again, I emphasize with these boundary conditions, so that phi 1 is phi 2. And we have taken the evolution around a circle of period beta. So I don't know how to specify this, except that just saying this. This is in Euclidean time with time period beta. Is it clear? Or is there any question? If we want to compute correlation functions like the one we saw above, we just insert operators here in the trace or here in the path integral. No, because I say there is some overall possible boundary conditions.
Okay.
Yeah, so maybe I should repeat. So this is what the path integral is computing. Then now I decide that I start from a point in the Euclidean time series, I come back there. So at that point, when I do this, I have to take phi 1 equal phi 2 and tau 2 equal tau 1 plus beta. So here I will have just beta. So this is one step. And then what I do in the path integral is to sum over all possible phi 1s. Nothing depends on the boundary condition anymore. Sure. Yeah, the field can fluctuate. In the path integral, I have this measure. It means that I consider all possible paths, but the only conditions I'm imposing on the path, they start and end along this circle, so that the background has this, there is this circle, and I impose periodicity of the field. I consider only paths that are periodic, if it's a bosonic, antiperiodic, if it's a fermionic field, around the time circle. And I don't impose any other conditions, so I'm summing over all possible other boundary conditions, because I'm not imposing anything else than this. Is it clear? Phi can have any spatial dependence. I can then, okay, we can discuss, maybe it needs to have some prescribed boundary conditions at infinity. Here I'm just discussing the boundary conditions along time. It's the usual path integral for the rest. The only difference is this periodicity or anti-periodicity in Euclidean time. Apart from that, is the path integral you know. Maybe you already know this one as well, but okay.
You are identifying phi 1 with phi 2 in the time direction, but they could be at different points in space. No?
Say it again, sorry?
They could be at different points in space. So phi 1 could be a function of tau and x, and phi 2.
Phi 1 is the boundary condition at time tau 1, so it's a profile in the full space. I need to say, I don't know, the field is 0 everywhere, or it has some profile that I choose. And same, originally the same is 2, so I prescribe what's the field profile everywhere. But then, after I've done this trick, this prescription is gone. I'm just left with the periodicity in Euclidean time. Okay, this is how to define the canonical partition function at finite temperature beta, either in the Hilbert space Hamiltonian formulation or in the path integral Lagrangian formulation. We will need also some slightly more complicated partition functions that are those that are relevant for the grand canonical ensemble. So what is the difference between the canonical and grand canonical ensemble? That we also have some chemical potentials in the system. We are, for instance, we may have an electrostatic potential. Let me call this chemical potential. We raise the system at some potential phi, the electrostatic potential that we saw in the Kerr-Newman solution. It was called capital phi. And we want to see what's the thermodynamics of this system at this potential. So the difference is that the electric charge of the states will not be fixed because we have a potential. While so far, we didn't, in principle, we didn't introduce the electric charge, but it could have been fixed. The actual name chemical potential comes from chemical potential in more concrete experiments where the particle number is not fixed. When you have a chemical potential, the particle number is not fixed. And this is the generalization of that in terms of the electric charge, or now I'm going to consider a chemical potential for rotations, that is the angular velocity. Let me do one step after the other, so maybe it's more explicit. So you're probably familiar with all this, but maybe I just recap. In statistical mechanics, you consider different statistical ensembles. There is the canonical one, which is this one fixed temperature. Here, the energy is not fixed. The different states have different energy. What is fixed is the temperature. You can go in the microcanonical ensemble, where each state has, each microstate of your statistical ensemble has a fixed energy. And we can go even more general into this grand canonical ensemble, where the temperature is fixed, the energy therefore is not fixed, and we introduce other potentials. We introduce this electrostatic potential or the angular velocity, and therefore the associated charges, that is the electric charge or the angular momentum, for the two examples I'm interested in, are not fixed. The microstates carry different charges. What is fixed is the corresponding potential. So we want to do QFT, no more in the canonical ensemble, but in this grand canonical ensemble. For this, we need to specify chemical potentials. So we need to assume a bit more than so far we assume translation invariance. So time translation invariance means that there is a conserved quantity that is the energy. And since we fixed the temperature, we decided that each microstate didn't carry the same energy, but what was fixed was the temperature. Here we need to assume that we have some other conserved quantities. For instance, the two that I just mentioned, electric charge and angular momentum. And we want to describe a system where the microstates can fluctuate, that is, have different charges, but we fix the potentials associated to them. So the density matrix, the one that you would always see when you do statistical field theory, is again e to the minus beta h. But now that's not all, because we have these extra contributions. So we have the angular potential, or let's call it angular potential omega. And we have the angular momentum, J. So this is an assumption that angular momentum is conserved in my system. If I have in curved space, I will need to require that there is this axisymmetric space-time. Otherwise, angular momentum will not be conserved. But let's assume that. So we have it. We can introduce this. And we can also introduce the electrostatic potential capital phi. Let me call it just electric potential. Everything here is static, or at least there is no time evolution, so it's a constant. And Q is the electric charge. So we are introducing this because this will be relevant to describe our black holes that may have a mass, but also some angular momentum and some electric charge. The Kerr-Newman black hole had carried all these conserved charges. But we are not, so far there's no black hole. It's just QFT in a fixed background. I'm even considering a flat background, but you can also assume it is curved. The only important thing is that there is periodicity in time. Now let's see how this question of periodicity in time, this property, is possibly modified by introducing these extra quantities. If you want to do, so this is very general, so it can be applied to experiments or not. But for what we may be interested in doing, it's important on the one hand because this, for instance, rotation is certainly something that is relevant for black holes. But also this refines your partition function, because the partition function that I'm going to define now is the grand canonical one, and it does not depend on beta only. So it's a richer function. It depends on all the potentials. It's the trace over the Hilbert space of the theory of e to the minus beta h minus omega j minus phi q. It's always the trace of the density matrix. But the density matrix now contains these extra things. So what does it mean? I trace each state, let's say it's a quantum system, so each state in the system carries some energy, some angular momentum, and some charge. And so I need to implement the respective eigenvalues, and then I trace over all the states. What remains is a function of these chemical potentials here. So I have a function that is more rich than the one that I had before, because it depends on 3 variables than just one. So this is the grand canonical partition function. H, J, and Q are charge operators. They act on any state. So here trace means that I have any state here and any state there. I have this operator inside, and they act on each state. So if this is a basis for, if I diagonalize these together, each of these will carry some definite quantum number, and I weight my trace with not just e to the minus beta times the energy, but this combination. It's as simple as this. Okay, now we want to repeat this exercise of the Green's function. We can do that, but you see now it's not exactly the same story, because we still have this evolution. I mean, we still recognize this as evolution in imaginary time. H still generates time translations. But while we evolve in imaginary time, we also rotate a little bit, because we have this extra contribution. And we also perform gauge transformations, because the charge generates gauge transformations on the states. So when we somehow come back to the original point, we are going to derive some periodicity of this type, but it will not just be this, because we have something else that acts while we move around the time circle. So we will have some rotation as well, for instance, and some other effect due to the charge. So I would say just do this as an exercise. What I'm going to give just the final formula. You just need to repeat these steps, exactly these ones, but adding the extra operators here, the action of the extra operators. And recall that, okay, time evolution is this one, but evolution along the angle along which you have angular momentum is the same. I mean, you also have e to the I delta phi j, or e to the minus I delta phi j, and this is O of phi plus delta phi. Use the same trick, but for angular momentum, and then you should recall how the electric charge acts. What you get, you can see it's quite intuitive. I write down just the result. We always have minus 1 to the f due to the fact that we may have fermionic or bosonic operators. Then we have e to the q beta phi. Let me comment on this in a second. Now this is no more the thermal Green function. It's always thermal, but it also depends on the other angular momentum, the other chemical potentials, sorry. So beta, omega, and phi. G of beta, omega, and phi. So I have the evolution in imaginary time. Then we have, suppose that the angular momentum generates rotations along phi, some coordinate phi. So I emphasize phi here as well. And the other spatial coordinates. So again, we need, since we are assuming this is the phi translations are gives rise to a conserved quantity, it means that again we can assume that we can infer that the Green's function depends only on phi minus phi prime. It's the same argument as for time. So the Green's function will depend just on t and phi, because we can set t prime and phi prime to 0. Just same identical argument as before. So this is the result for the new periodicity conditions on our Green's function.
Phi will be the angle between x prime and x, or
Okay, sorry, let me specify better the notation. In principle, we have, say, 4 space coordinates. We have t, phi, in Kerr-Newman. We had t, phi, r, and theta, right? We have time and three space coordinates. Now we want to emphasize these two because we have translations along t generated by the Hamiltonian h, translations along phi generated by angular momentum j. The other two coordinates are not important and could be, I don't know, it could be in 10 space-time dimensions. So I call these x, the other ones. Now I'm considering the Green's function 2 points, operators evaluated at 2 points. So I would need to have t, phi, x, and t prime, phi prime, x prime. But we know that the Green's function can only depend on t minus t prime because I have time translation invariance. Can only depend on phi minus phi prime because I have translation invariance along phi, the angular direction. So I can set t prime and phi prime to 0. So the only variables that enter are t, phi, x, x prime, and this is the notation I'm using here. Clear? Are there questions? So try to do this. It's a simple exercise. It's just repeating more than once what we have done, what we have seen for the canonical case. So what's the meaning of this? That when we go from t to t plus I beta, at the same time we rotate by this amount in imaginary angle phi, and nothing happens to the other coordinates. And the charge induces this transformation. So charge means we have I called it gauge before, but let's not say it is gauge, because charge is, we have a global U1 symmetry. I have not gauged it yet. I will do this in a moment, but this is not gauged. So it just implements the transformation, the charge Q implements the transformation, the global transformation along weighted by the charge associated to the Green's function. I'm assuming here that the operator O, the time for which I'm evaluating the Green's function, have charge Q under the charge operator capital Q. So this is the eigenvalue. And this appears here. You can prove this. In the same way as you have these shifts, you will have a shift in the internal symmetry associated with the charge that appears here as an exponential factor. Is it acceptable, at least, for those that have not seen this before? Okay. So now we would like to, again, continue the Euclidean time, continuum t to Euclidean time. But if you send t to I tau, okay, here you get a nice periodicity, but here you still get an imaginary angle periodicity, which is bizarre. And also it's a bit cumbersome to interpret this space where you go around the time circle, but at the same time, before identifying your fields, you need to also rotate in some angular direction. So before going Euclidean, let's do a change of coordinates that will simplify things. You can also play with this. You can stay with this. There's no problem, but it's slightly simpler to perform a change of coordinates. So, okay, before doing that, let me just say, okay, the conclusion is that since the Green's functions all have this periodicity, we have this identification. That is what I just said in words. So the space-time coordinates are identified in this way because all the functions have this periodicity. So we conclude that we should identify the space-time coordinates in this way. And moreover, with the correlation functions be identified when we compute the correlation function, in addition to identify the time coordinates and the space phi coordinates in this way, we need to weight this two-point function by the charge of the operators we are considering. But again, I was saying, let's change coordinates. This simplifies the identifications. Okay, for those that are not staring at the notes, what would you do what change of coordinate may simplify the situation? Do you see what is something that helps? What is disturbing is this, no? Compared to the previous situation. You would like somehow to go back to the previous situation where you can identify the time, go Euclidean, so analytically continue t in I tau, and then just identify tau in tau plus beta without weird i's. So you need to get rid of that. No? No ideas? Say it again?
Something like t plus phi over
3. Ah, t. Yeah, something like that. Not exactly, but something like that. I can introduce new coordinates phi hat, and t hat. But the non-trivial one is phi hat, is phi minus omega t, and t hat is just t. But it's good to distinguish between the new and the old t. I mean, here they are just the same, but when I compute d over dt hat, this is not d over dt. So it's good to distinguish, because you have a contribution from there. We will do this. But let's, for the moment, just do this change of coordinates.
Phi is an angular coordinate, right?
I have not, yeah, maybe you want to say it's, I should have it. Yeah, the rule here is that, so a priori I could say phi is already identified up to 2 pi, and now I shifted by t. What happens to phi hat? So in this case, you may see, you can see that the periodicity of phi hat is the same, doesn't change. But more generally, when you do this, when you play these games, you relax all the periodicity on the coordinates that you had before. You say, I do this locally. I don't know what is the global conditions on the coordinates. I do that. I then stare at the new metric, new fields in these coordinates, and I decide after what are the regularity conditions, if I need to impose some regularity conditions on the new coordinates. So this is the general rule, but in this case, okay, it doesn't even...
And is the periodicity of the two-point function consistent with phi, is identified with phi plus 2 pi?
So the question is whether the periodicity of the two-point function is consistent with this. Yes, here maybe it's not too clear, but what I'm doing here is not that I'm doing a tour along the phi circle, because I also have, if you want, here I also have another identification that is phi plus 2 pi that leaves t invariant. I don't move along t. I don't move along t. T phi is also identified with t phi plus 2 pi. This may well be the case. Let's say it is the case in Minkowski spacetime, where phi is the coordinate that we have been using so far. But I also have another identification that corresponds to moving along the t circle. Okay, it's not a circle yet because I have this imaginary period. But when I do the tour along t, I also need to rotate along phi. Then you can ask, okay, if this is only defined modulo 2 pi. Okay, yes, it's true. But I want to do this change of coordinates because things become more neat in the new system. So the identifications that were a bit uncomfortable there become, the identification is just, for the hat coordinates, is just t is identified with t hat plus I beta. And then phi hat remains invariant. Yes, it's correct. Yeah, because when I go around t, phi shifts, but then t also shifts, and these two compensate each other, right? So phi hat does not shift because I have two shifts that. Oh, since it's wrong, let's see. Phi goes in phi minus I beta omega, and T. Let me see. Let's check, because I've been messing around with these signs because I wanted something. So, okay, phi minus omega t goes into phi minus I beta omega, and then minus I have omega t here, omega t, and E beta. So this is, I should put probably a plus here. No, or in the change of coordinates. Let's do this. Probably I forgot to put the plus in here in the change of coordinates. Is this what you were saying? Yeah, probably you're right. I'm sorry, I messed around with these signs because of some reason that is not important here. But I may have forgotten to change the appropriate signs where it's needed, even in the notes. Okay, does everything work out? Anyway, the general rule is to choose the change of coordinates, whatever is the sign, but to choose the change of coordinates in such a way that the identification only involves the new time and not the angular coordinates. Yeah, this is phi hat, no? Phi hat. What is the question? Sorry. Oh.
Plus omega t and minus omega I beta. So they all cancel, and then phi minus phi plus omega t remains. So
Okay, you're right. Sorry for that again. So that was okay before then.
No. It's right now, but you forgot one piece in the check. But it's okay.
Okay. Give me the piece.
Cancel the t there.
Okay, I forgot the piece with the t, okay. Yeah, sorry, I forgot the piece with the t. Yeah, I shouldn't have written omega t I beta. Yeah, there is the piece with the t that reconstructs phi hat. Sure. Then this is, in the end, is just phi hat. There is the piece with the t. Minus I plus I omega t. That's it. Okay. It's almost time for a break. That's now let me just say, can you give me 10 minutes? Yeah, I would like to conclude this discussion of the partition functions. I'll erase this. So before we had this Hamiltonian H, and not before, we still have that. And it generates translations along T. So in some coordinate representations, it's really the Killing vector T that generates translations along T, so del T. The angular momentum, similarly, is something like minus I del. They always come with the negative sign. And so if we compute the generator, the operator that is H minus omega j, that is the one that appears here, no? This one. This is a sort of translation operator, but translates both along T and along phi. So let's look what is this. These combined derivatives. So we have del t minus plus omega. The signs are okay, yes, because there is this minus I, del phi. And this is del t hat. This is what I was saying before, that it's important to distinguish between t and t hat, because the derivative with respect to t is not the same as the derivative with respect to t hat. I guess I don't have to prove this, but just use the change of coordinates up there, and you deduce this. So in the new coordinates, in the hatted coordinates, the new Hamiltonian is not, the Hamiltonian is no more h, is this one. So the new time, t hat, is the translations along the new time are generated with using, if we still use the old operators, by this omega h minus omega j that we may want to call h hat. At this point, we have somehow understood what we have done. We are really evolving in a different time direction, that is h hat, degenerated by h hat. So it's natural now to analytically continue this time, this t hat coordinate. And now the analytic continuation of t hat in equal minus I tau hat is such that the identifications are those we have just deduced. So with some pain, but we did. So tau hat is phi hat, and phi hat is identified with tau hat minus beta. I think the signs should be this. This is the reason why I was messing around, because I had the minus here. And phi hat. But okay, plus or minus doesn't make a big difference. We are still identifying things, either we evolve in one direction or the other. Is it okay? So in principle, you could say, yeah, nice. This is nice. Basically, we are somehow back to the canonical ensemble, in a sense. We are back to what we have done before, modulo the electric charge that just weights this Green's function. But from the point of view of space-time, we are now have a new time. So the temperature is still the temperature, doesn't change. We have identified just the coordinates in a different way. So where is omega? There is no omega anymore. I have beta, here is beta, is still the length of the thermal circle in these new coordinates, but I've lost omega. So is this, can I say, okay, this shift by omega I could even not do, is the same or not? Of course not, otherwise I wouldn't have spent all this time, but where is this? Where is omega? So we have changed coordinates, right? Jacobian of what? Of the path integral? No, it's even more simple. I mean, it's even more simple in the background. No, we had a background before. Say the background it could be flat space, but since I want to apply this to black holes, let's write a more general metric than the one of Minkowski. So before, we had this metric, suppose. A sufficiently general metric for us is some function of r and theta, dt squared, plus another function of r and theta, d phi squared, plus the rest. The rest is not so important. Here we are playing with t and phi. And the other t, the d theta squared, d theta, d phi, not too important. And after we change the coordinates, what happens? It happens that the metric is not the same. Of course, it's just a change of coordinates. Locally, it doesn't do anything. But the global identifications are different, because it's at this point we are identifying tau hat with tau hat minus beta, and not tau, that is the continuation of t, with t plus I beta. There are two inequivalent coordinate identifications, because we have seen in the original coordinates we not only have to identify t plus I beta, but we also need to implement this shift. So the two identifications would not be the same if we identified tau hat with tau hat minus beta and tau with tau minus beta. So the two spacetimes are have different coordinate identifications. And after, so it's not the same, it's another metric. After, locally they are related, but globally not. Minus f dr theta dt hat squared plus h of r theta d phi. Now what's the sign we have taken? Phi plus omega t. If I use phi hat minus omega t hat, right? Minus omega t hat dt hat squared plus rest. Okay, and this is still t hat. I would now like to continue the space-time to imaginary time, so that this becomes plus. So this is the same as plus f d tau squared plus h d phi hat. Now t hat is minus I tau hat. So I have plus omega I d tau hat squared. So you see that we have a basically we are in we have now have a matrix that looks Riemannian. For instance, if I compute the determinant, this piece is not important for the determinant. It is positive. It's not negative. But I have some imaginary components here, some shifts in these angular coordinates that are imaginary after I've gone in Euclidean space. So it's not really a Riemannian metric. It has some imaginary components, and we have to play with that. Unless we want to do yet another step and say that we analytically continue omega, that here is real, to an imaginary value, so that we come back to a positive definite metric which is real. So this can be done. We can assume we can analytically continue omega to imaginary values. We do all the computations in our nice real and positive metric, positive definite metric, and then after we have obtained what we wanted to obtain, we come back to the original omega, analytically continue back. So these are tricks that you always play in this Euclidean quantum gravity approach. And this is as far as the angular momentum is concerned, so the rotations along the angular momentum, we have treated them, changed coordinates, found the right identifications. We still have to play with the gauge transformations, in the sense so far we don't have gauge transformations. We have this global symmetry that introduces, every time we go around the time circle, it introduces this extra weight up there in the Green's functions. So we could say all the fields in the path integral are identified. So that up there is in the Green's functions, but in the path integral we would say the same. We are in this space-time, we have defined the identifications up there, and in addition, when we do a circle, we would go around the circle, the fields are identified modulo this U1 transformation acting on them. Each of them weighted by its charge, Q. So it's a bit, again, we can do that. It's a prescribed boundary condition. There is the action of some charge on the field when we identify the field after we have done the tour. But we could do something different so that we get rid of this perhaps annoying or confusing identification. So what can we do? Well, I already said that, but maybe someone can motivate. why, if I gauge the transformation, I can do something useful. Sorry, I'm taking some time, but I would like to finish this part. Yes. So the answer is there is a background gauge field. Yes, because, okay, let's see. If I introduce, I have a global U1, and the global U1 is defined in such a way that it acts, so up there is on the Green's functions, on the fields it would be the same. Wait, let me just check. So how should I write it? So far we have that phi tau hat minus beta. So I have this identification that I have to implement on the fields. So phi of tau hat minus beta goes into phi of tau hat, but there is this action of the U1 charge, e to the, I'm assuming it's U1 just to make it simple. It could be a bunch of U1s. It would be more complicated. Let's take it to be a U1. It's the one it's up there. This is the identification in the presence of the electrostatic potential. And let me say this is old, because now I want to do something more. This is what we have so far. Now, I just check signs and all that, should be okay. Now, we want to, let's say, we gauge this transformation. So we introduce the gauge potential A, but we don't want to quantize this or so. It's just weakly gauging. It's an external field. It's treated as an external field, but we say it's an external field that couples to this current that for which capital Q is the charge. And once we have done that, we can remove this factor by the gauge transformation. This is what we want to do. We say, this is the situation in some gauge. Now I change my gauge. I can remove this, because the fields are charged under the transformation. I remove that, but of course, the price to pay is that the gauge transformation introduces a background gauge field that was not there so far, but the background gauge field that I've introduced because I want to gauge the transformation will show up in the transformation, because everything must remain covariant under this new gauge transformation. So let me do, I define phi nu, the gauge transformed field, e to the I q lambda phi old. Phi old. This is a gauge transformed field. Phi nu is phi in a different gauge. It's just the way the gauge transformation with parameter lambda acts on a charged field. Do you agree with this?
Sorry, one question. I'm still lost because we proved before that the green function is indeed periodic, but why is also the scalar field periodic?
The Green's function is the Green's function for any operator, but the operator O could be this scalar field. So all the Green's functions have these periodicity properties. It means that the fields phi have these periodicity properties when I evaluate them in the path integral. So the step I'm doing is that I'm using this phi in the path integral to reproduce the same Green's functions that have these periodicity properties. I need to put into my path integral boundary conditions such that when I go around the Euclidean time circle, I get this extra factor. The identifications is up to this. Is in order. I need to do that in order to reproduce Green's functions from the path integral approach that have this property. Okay. So I define a gauge transformed field. Lambda is my gauge parameter. And then I wisely choose the gauge transformation. I choose gauge parameter lambda is minus I tau hat. So you see, it depends on tau, so it's not a global transformation. It depends on the coordinate, so it's a local gauge transformation. But it's such that when I go around the time circle, it offsets this, unless I missed some signs. But it should work. So the phi nu of tau hat minus beta is identified now with phi nu of tau hat. I'm assuming here the field is bosonic. If it was fermionic, there would be a sign, but the sign we know how to implement. So gauge here, what I'm doing is a gauge transformation. And the effect of a gauge transformation is also to shift the gauge field. But you could say, okay, there was no gauge field, but it will appear in the covariant derivatives. So in general, a gauge transformation does A nu is A old plus D lambda. Now, A old was 0. We didn't have any gauge field before the gauge transformation. But the new gauge field will not be 0 because we have D lambda. And since the gauge parameter depends on tau hat, we will have d tau hat there. So the new gauge field will be minus I phi d tau hat. Again, it has an imaginary component, and moreover tau hat, sorry, this is tau hat. So this is also compactified because tau is periodic. So what people say is that you introduce a line for the gauge field on the Euclidean time circle with an imaginary component. So final statement. Yeah, phi is constant. Yeah, phi omega is also constant. I can erase this. So the final statement is that I can convert all this or summarize all this in the path integral approach in the grand canonical partition function, which will be partition function z of beta omega phi, which is the one we have defined up there, beta omega h minus omega j minus phi q, which is also the same in the path integral as simply this path integral so the action now, the Euclidean action depends on the dynamical fields phi I'm integrating over, then in the and gauge field that I've introduced by the gauge transformation, and also the metric. Let me write it G hat, in the sense that it is this metric here with this prescribed identification of the coordinates. So in here, there is the information about the background. The background is this one I've introduced. There are some specific prescribed identification of the coordinates. There is this Wilson line for the gauge field. And then I have either periodic or anti-periodic boundary conditions for the fields, because now we have found these boundary conditions are these ones for the fields. They are simply identifications for bosons and identifications up sign for fermions. And this is my prescription. So the prescription is that QFT, the QFT observables, including the partition function, evaluated using this path integral with these boundary conditions, always you have to specify the boundary conditions in your path integral, computes the grand canonical partition function for a system at temperature 1 over beta, angular potential omega, and electrostatic potential phi. So, and now we will apply this to black hole physics in the remaining half an hour after the 10 minutes, maybe no more than that break, so that we don't finish too late. Okay. So it seems that the coordinate identifications and the signs there don't work out yet. So I will recheck and fix them in the notes if needed. probably it will be needed. Or each of you try to work out your final answer, and we will compare later on. So I don't want to spend more time now also because I would mess it up again. So I will think about that and fix it in the notes. At most there are signs, nothing else, hopefully. Okay, now we have seen some formalism and introduced the grand canonical partition function, which generalizes the canonical one to the case where we have this angular and electric symmetry. And we would apply all this to black hole physics. So we have seen from the computations of yesterday that black holes have a finite temperature. So it's a good idea to consider QFT in a curved background, in the curved background of the black hole. So what we had seen yesterday was we assigned the temperature to the black hole via this reasoning. We have a quantum field phi, so a bosonic scalar field, for instance, phi, that is defined on the black hole background, and we quantized that, and we saw that the observer at infinity sees thermal radiation. So the observer at infinity would just do quantum field theory at finite temperature to describe this field. And then since everything is at equilibrium, in that situation that we studied of the Schwarzschild geometry, we concluded that the black hole also must have a temperature, because equilibrium means that everything is at the same temperature. So we studied the field out of the black hole, and we concluded there's finite temperature. Since there is equilibrium, the black hole also has a temperature. In this situation, it looks natural to study the canonical ensemble, because everything is at equilibrium at finite temperature, and we can describe whatever is out of the black hole, not the black hole itself, not the dynamics. In the canonical ensemble, everything is at equilibrium, but we can describe the properties of the outside field by this machinery. So this is what we want to do, and from this infer by this argument of equilibrium properties of the black hole itself. So we consider the Schwarzschild. Let's start from the simplest case, the Schwarzschild geometry in this Euclidean space. So have you already, I guess, maybe many of you already saw how the Hawking temperature arises from this. It's actually the easy way to get the Hawking temperature. But okay, let me go through it. I'm not sure. Is it, just let me know, is this familiar to how many of you? How to deduce the Hawking temperature from, not many. Nice. So instead, I repeat, instead of considering flat space, I consider the Schwarzschild background. The Schwarzschild metric, after I do t equal minus I times tau, is the following. Is the same already considered, but with the Wick rotation to Euclidean time. Okay, and nothing has changed except for the here, because this is tau and not t. So I'm now in Euclidean. Yes.
There is the square there is wrong, right?
Yes, sorry, thanks. Thank you. Sorry. No square there. And now let's see what is this. Let's take first large R at large R, we have here there is a circle. This part that depends on R is irrelevant because it becomes very small compared to 1. So the metric is basically d tau squared, so for R that goes to infinity, d tau squared plus here we have the metric of flat space. D squared plus R squared d omega 2. So this is the metric on R3. And this is the metric on flat space again, but since we have this identification of the tau coordinate, I separate this from R3 because actually this is S1. So we are on S1 times R3. Okay. And so far, I anticipated a bit the fact that I have identified this. So far, we may even work with R. But let's say if we want, we can do this, because after all, we want to work at finite temperature. So it's something that maybe we will need to. If we want, we can do it. So let's say for now, it's S1 or R. It doesn't change, because I can choose the periodicity. I can choose the periodicity to be infinite or not. From what I see at infinity, there is no constraint on this identification. So where is the possible constraint on the identification of the coordinates coming from? It will come from the near horizon region. Okay, so I'm trying to make the connection with what we have seen so far. We have seen that quantum field theory at finite temperature requires identification of the Euclidean circle. You may say, I already know that I am at finite temperature here because I know there is Hawking radiation, I know what's the value of the Hawking radiation, so I know what's the periodicity of beta that I have to require. But suppose we have not done Hawking's computation. We are here, we are at infinity. Maybe we have to do this identification, but it's still not clear. Now we want to do consider regularity of the geometry everywhere, not just at infinity. This is just a consideration asymptotically, that it is made asymptotically. So we start reduce the value of R. So of course, something particular happens when R is Rs. So in the same way as in the Lorentzian case, here this part of the geometry goes to 0, this d tau squared component of the metric goes to 0, and this one blows up in these coordinates. Suppose we go beyond that. Actually, you don't find the singularity, but you find that the signature of the space-time changes dramatically, because if, where can I write? For R larger than Rs, the signature is minus, plus, plus, plus. For R smaller than Rs, I will not find singularities, but I will find that there is this different signature. So I'm really, for R smaller than the Schwarzschild radius, I'm describing a different space-time. It has different space. It has, sorry, this is plus. It has different signature. And so I should really consider it as a disconnected part of the space. So I'm only, because of this consideration, I can consider R only between Rs. Now we go and see what happens in Rs and infinity. I stop there. So this, whatever was a problem before, the singularity and all that, is excluded in any case from the geometry.
Why do we see automatic this split signature for R less than R?
You should consider this as a disconnected part of the space. So all possible issues arise from R that approaches the value Rs. Any point of these is there because before nothing special happens when we are at intermediate values of R. So let's expand near to R equal Rs. Let's zoom in there. So change coordinate. So what I'm taking R equal Rs plus something small. Rho is the new coordinate. I'm replacing R with rho. And maybe rho squared is more convenient. It's just for convenience that I call it rho squared. And I take it small, so that I'm around Rs. So you see from here that dr is just 2Rs. And the relevant function that is 1 minus Rs over R is rho squared over 4Rs squared. So I can write the matrix at leading order in this rho expansion. Think about rho as a small parameter. I can expand all the functions that I have. And I replace dr with d rho.
1 minus Rs over R is rho squared over 4 plus R. Yeah, but then R is Rs plus R over rho becomes higher.
Should we do this expansion?
Yeah, it's just that it's missing plus dot dot dot.
Ah, yeah, sure. This is at leading order. So, yeah, everything is, this is just exact from here, but this is a leading order term, because I'm interested in only what happens around Rs, so I do the expansions at leading order. So, this is actually the only expansion I have to do. All the rest is simple. So let's see what we get. We get, for the tau squared is rho squared, d tau squared over 4Rs. Let's see if it works out. D rho squared plus Rs squared. So I have the function. We just say that the function, there was a square here, right? Yeah, seems okay, no? Not sure? Or sure? Hopefully yes. So this is the leading order. So here I took just the leading order terms, which is Rs. In principle, there are the corrections, but this is the leading order term that multiplies this part of the matrix. And for d rho, I have just this, because I've offset this 4Rs squared with the rho squared, with the function that was there. So this should be the answer. And what do you see? What can we conclude? What is this matrix? So for this part, it's just the part of a matrix on S2 at radius Rs. This is fixed, and it's a direct product with the rest. Is independent of the value of tau. So this is there, and we don't touch it. And now we look at the rest. What is this? What is this matrix? Yeah, it's the matrix on R2 in polar coordinates. R2 in polar coordinates. But to be precise, so locally it is the matrix on R2 in polar coordinates. But we have to be careful about what happens when rho is very, very small and goes to 0. So here we may have a singularity if we don't identify tau, which is like an angular coordinate here, in the appropriate way. So for we are using some polar coordinates. Just to be very, very explicit, I could say I take an angle psi equal to tau over 2 Rs. So I would have a rho squared d psi squared plus d rho squared, which is really the metric. So I would have d rho squared plus rho squared d psi squared. But I need to make sure that psi is identified up to 2 pi, because otherwise I have singularity. So rho measures the distance from the origin. The angle pi, this is the angle for any point, this is rho, and this is the angle psi. So if I identify this, say, with this, so I identify things, but not up to 2 pi, up to some other angle, any other angle. Let's say I choose this angle to be theta. Then identify psi with psi plus 2 pi minus theta, just because I choose to do that. This is a singular space, because I can, if I embed this in 3 dimensions, because I want to somehow draw this and connect the 2 things. So I can do this on a piece of paper. I cut some wedge, and then I put it in 3D, and identify the space. So I get a cone, right? With some deficit angle, which is theta. Is determined by theta. So there is a curvature singularity here. How can I see the curvature singularity? Well, the way to deal with singularities is to smoothen them out and then take the limit. So for instance, this space, I can regularize it by taking something of this type. Now it's smooth. And this new thing that I attached has a radius epsilon, say. So I have a cap there. And then I compute the curvature of this. There will be some curvature here. All the rest is flat. It's just the cone is flat. And here, so it's flat. Now it doesn't look flat because I embedded it in R3, but the intrinsic, the Riemann tensor would be 0, except for this region. Then I shrink epsilon, so the curvature is concentrated at the tip. So there is a delta function for the curvature here. This is a delta function. And this singularity we don't like, because there is a delta function in the curvature. It wouldn't solve the Einstein equations in the vacuum, because the Einstein equation in the vacuum does not allow for anything. There is a 0 on the right-hand side. So singularities of this type, in this context at least, don't make sense. So we want really to identify psi with psi plus 2 pi, no deficit angle theta, and therefore the original coordinate tau, so I write it here, R2 in polar coordinates, yes, it's correct, but in order for this to be really true and have a smooth space, we need to identify tau with tau plus, so 4 pi Rs. Because psi is identified up to 2 pi, and tau is identified up to 2 pi times 2 Rs, which is 4 pi Rs. So beta, now we have the length of the time circle, Euclidean time circle, it's beta, we call it beta, is 4 pi Rs. But this really deserves some more space, so I do this here. So this is what we have deduced. We have beta is 4 pi rs. And for the Schwarzschild geometry, this is 2 pi over kappa, where kappa is the surface gravity of Schwarzschild, which was 2 rs, 1 over 2 rs. And we conclude that this is the same as the Hawking temperature that we deduced by a completely different computation. This is the same result that we obtained yesterday. Hawking temperature was kappa over 2 pi. So even if from infinity we may have wanted to keep the time direction not compact, or maybe we would have accepted to compactify it, but with any length, any period beta, we are seeing that regularity of the geometry near to the point where it caps off, that is near to the point where r is equal to rs, regularity there requires that the length of the time circle, so first the time circle is compactified, and then the length is precisely 1 over the Hawking temperature. So, by all what we have seen before, we conclude that whatever quantum field theory we do on this background, we must put it at the temperature 1 over beta. And this is a very simple trick that works in great generality. Suppose you are in 6 dimensions, you have ADS black holes, they rotate, they have different charges. Computing the temperature may be complicated, but regularity in the near the horizon is much more simple. So this trick, which here we have seen in a simple setup, generalizes. Indeed, now we are going to see how this also gives correct answers for a bit more general black holes. Was there a question? Yeah.
Here we are starting with the Schwarzschild metric in the Euclidean metric in the Euclidean signature.
Yes.
And then we perform a priori naive change of coordinate, simply to see what's happening near the singularity.
Yeah, the change of coordinate is just for studying the near horizon.
And given that I start with something that has really singularity, because the Schwarzschild metric, the coordinate of the Schwarzschild has a singularity. And then I'm instead imposing that these two coordinates should not have that singularity, because indeed the singularity rho equals 0 is precisely the singularity at the horizon that we will find in the Schwarzschild coordinates. But it doesn't seem to my coherence, because every time that we change coordinate and we require not to have a singularity, in our mind we are extending the solution, something that here we are not doing, because we're considering only the exterior of the black hole.
We are studying the exterior of the black hole, including the point where it caps off. We are including that point. S is included in the geometry. I want thing to cap off regularly because I want to have a honest solution to the Einstein equations, although then I consider it as fixed. But I want to start from a honest solution of the Einstein equations, and we saw that deficit angle would not satisfy this condition because of this delta function there.
So
I don't know if, is this what was exactly the question?
Can this trick be, like, it's like saying I want to extend my solution just to include also the horizon and period. Is it this true?
It's saying I want to do something like QFT at finite temperature. I need to work in Euclidean space. I work in Euclidean space, but I want this to still be a solution of the Euclidean Einstein equations. Forget about horizon or singularity at r equals 0. This was Lorentzian. Now we are in a new setup, and we need the space to solve the Einstein equations, the Euclidean Einstein equations, and these are the conditions you have to impose. There is no extension. It's as clean as that. The fact that the space ends there, in a sense, it's dictated by this fact. But let's see what's the picture. Maybe I can draw a picture to show this more explicitly. So we have S2. S2 is always there, and let's live with that. Then the rest of the space is this R. It becomes R2 close to the tip. But globally, if I take this space and I impose this periodicity, it looks like a cigar. No, it's like a cigar. This is tau. This is R. R extends up to infinity, so it's an infinite cigar. And then when I go close to R equal Rs here, it closes off, and it closes off in a smooth way, because very close to there, the geometry is the one of flat space, that one up there in polar coordinates. So it's smooth. There is no conical singularity, because we excluded that by requiring the appropriate periodicity. So the geometry that we are studying is cigar times S2. It's a honest solution of the Einstein equations in the Euclidean space, regular. We can do QFT on this space.
Can I ask you another question?
Yes.
Yesterday we concluded the radiation, temperature
Yes.
from quantum field theory to space-time. But
Yes.
here it seems that you obtain the temperature in a completely classical setup.
Yes, it is classical. But it uses all this machinery that we did before. So it uses the fact that I have quantum evolution generated by the Hamiltonian, and then I do the analogy with the Boltzmann factor. Classical in statistical mechanics, but from the point of view of QFT is QFT. I mean, I'm doing QFT on this space. Although, so before we were doing QFT, so we were doing Green's functions and all this was QFT, but the final conclusion we had was that we had to identify the coordinates. This is, you can call it classical if you want, it's just a condition on the background. And here is the same. We are doing quantum field theory, but okay, you may say the real constraint I'm imposing is regularity of classical geometry. Yeah, that's correct. It's why it was not obvious. Hawking didn't derive the temperature in this way. It was done later by himself again. But I think it was Hartle-Hawking and then Gibbons-Hawking. What I'm going to discuss later on is mostly Gibbons-Hawking and Perry and others. It's still physics from the 70s, but good physics from the 70s. So it's time to stop. We will go on with this later on at 3. Yes, let's start again at 3.